Buzz from Google Cloud. Like I mentioned, I was a producer for a very long time, and I like to think that I've created a lot of the problems we're trying to solve now in the cloud as a producer. But what I'm here to talk about today, aside from lobbying to be the president of the Andrea Callis fan club, is to talk a little bit more about Fixity. And so, and this is specifically how we're handling it in Google Cloud, but I wanted to just kind of show you where we're at with this because, as she mentioned, it's a process right now, and it takes a little bit of cajoling to make things work. So we talked about what Fixity is, this idea of ensuring the integrity of a file, essentially, and verifying that it hasn't been altered or corrupted in any given way. And as she mentioned as well, it's typically done by generating a hash or some sort of checksum on every digital file in the archive and storing that hash along with the file. Now, some people go to the extent of doing Merkle tree approach, if you're familiar with Merkle trees, where you have your movie broken down into individual frames, and then those frames are grouped as shots, and those shots are grouped as scenes, and those scenes are grouped in reels, et cetera, et cetera. And it's possible to have hashes for each of those, if that's of interest to you. But as you can quickly see, the number of hashes that you amass gets pretty big pretty quickly. So in the case of a file, let's just sort of walk through the life of a file here really quickly. If you wanted to move a digital file from your server into cloud, first thing you want to do is generate that hash of the file at rest before it goes to wherever you're going to put it. So we use this particular command. You can use whatever MD5, in this case, MD5 command you want. You just have to make sure, like for example, any Mac users out there? The default MD5 command in there is not a base 64, so you'll come up with a number that freaks you out because it doesn't match the number that comes out of another system. So just make sure you're using the right one, but this command will get you there. So let's say, for example, we have a file that's called archivefile.movie, and we want to generate a checksum. So we basically are running this command locally, whenever the machine is, and then we come up with the checksum. So here's the checksum or the hash, in this case an MD5 hash that came out based on that particular file. And as Andrew mentioned, this checksum is then used for various processes. If you've written that tape already out to LTO tape, you're going to check it against those files. After you've restored those files or pulled them off tape, you're going to generate the MD5 and check it against the MD5 or C4, whatever you're using. So in our case, this is what happens. So you're going to generate this key or this hash, and then you're going to make a record of it someplace. So again, as she mentioned, you're going to have a digest of some a media asset management system or something, some place that you're putting all this stuff, where you then have to correlate it to the file. So now that you've identified the checksum for that file, now it's time to upload it to the cloud. So we've got the original hash that we generated on-prem, and we want to make sure that by the time it gets to cloud, it's the same checksum, right? So one of the nice things about working with file systems in the cloud and object store is we have a lot of flexibility as to what we can do. And as you're probably aware, if you're using cloud storage, it doesn't resemble our typical directory structures. We have what we call blob storage, and so it's a very flat hierarchy. But we want to be able to make sure that this is the file we're actually talking about. So one of the command lines we have a tool set. If you download the Google Cloud SDK, you'll get this gsutil, which is the utility we use when we're talking to anything that's in a cloud bucket on Google, right? So you generate this particular command, which is stat, and then this is the location of the bucket itself and the file you can see there. And then when I generate this command, you'll see what happens here. There's just kind of a brief report of this. It shows when it was pulled, what class of storage you're pulling it from, but then it shows this information, which is actually embedded into the file. So what it has done is it's taken the file as soon as it's written it to cloud storage, and it's generated a hash after it landed there, and that hash is now embedded as permanent metadata in the file itself. So now you have, to Andrew's point, you basically have digest information that's embedded straight into the file. So now that's an immutable object, you can't change it. And from now on, when you're doing a check against that particular file, all you need to do is read the metadata of that file to know that that's the same key. Now, one of the things that becomes very useful in this idea of an embedded digest is the fact that, I think Eric mentioned this a little bit earlier, but there are certain workflows now that used to say visual effects, for example, for a long period of time was a file name dependency nightmare. you would have gazillions of files, and they were all dependent on the actual name of the file to link this texture to that model, to this simulation, to that blah, blah, blah. And of course, when you unarchive something years later, if those dependencies aren't still there, things break. People are starting to look at this idea of rather than reading file names, they read file hashes. So now, as part of any process that you're using, you can read the metadata of the hash without retrieving the file. You can read the metadata of the hash to make sure that that's the thing that you were looking for before you go ahead and download it or ingest it or do whatever you're going to do to it. So what's nice about this idea of embedding it in the file is that you have access to it before you've done anything with it, especially if the files are large. And GCS objects, Google Cloud Storage objects, are immutable, and they can only be replaced with a fairly elaborate process. So if something does happen to this particular file and it does get replaced in some automated fashion, a new checksum is generated and embedded back into that file anyway. So now you have this ability to read the hash directly from the file itself. However, you can also now embed, and this is where it gets a little tricky, you can embed further digest information into the file. You have key value pairs that you can assign on your own, where you can decide what information is so valuable that it really does need to be part of the file. And then that information can also be immutable and added to that file name. So it's a really interesting way to have some way to index your files without any relationship to a media asset management system or any other kind of digest, because it's embedded in the file. Now, you could go crazy and have 1,000 entries of metadata in the file, but it's probably not that practical. So it's more a question of getting back to Andrew's point about provenance, for example. There are so many archives now that are bought and sold as commodities from studio to studio, and this idea of the metadata going with it is a Herculean task at best. So having some of this more vital information embedded in there may make that an easier process. One of the things to be aware of, you have different ways of storing these hashes, however you want to do that. And you could use some traditional database formats like a Cloud SQL back end of a database you're using, or BigQuery. If you have an enormous archive, say for example you're saving everything at the frame level, you're probably going to end up with billions of frames in a decent archive. So you'd need to be able to sort through that stuff relatively quickly. So something like BigQuery is going to give you a very quick response to find anything. So that's a good place to store these kinds of things. But it really just depends on what it is you're trying to do. And BigQuery is designed to be a petabyte scale database so that you can throw out a lot of stuff at it and be able to get it back very, very quickly if you need it. And it's a serverless application, so it launches and runs very, very quickly. It also has machine learning built in if you're trying to train models based on certain aspects that you're doing. That makes it a little bit easier to use as well. But one of the things I just wanted to mention is that some of you may be familiar with the NDSA, which is the National Digital Stewardship Alliance. I don't know if it was born out of the National Archives, but it was certainly part of the discussions at National Archives. And so they've defined this set of levels of digital preservation. And so when we're talking about out of the box, writing to cloud and performing a fixity check, we're really talking about these first two levels. I won't go through all the boxes, but essentially, the very first level of digital preservation is just to make sure that you have at least 2 copies of what you're doing, and you're checking your fixity on ingest so you have some record of what it is. And then it gets down to these finer levels of detail, which we don't really need to go into too much today, but this idea of access. Who has access to that file? Who should have access to it? Who can change that file? What superset do those files belong to? Those kinds of things are important. The metadata of inventory and location, extremely important. And the file formats that you can accept. Now, as Andrew mentioned, she hasn't run into a digital file yet that they can't read, but I'm sure some of them have been challenging. But you can still read it. But how big is that window of opportunity where you can still read everything? That's going to be a question. I have a feeling that window is closing. So with Google Cloud Solutions right now, we are able to just get you to the level 2 part without any additional effort, which is, we replicate the copies in various locations. On ingest, we're actually writing that information into the file itself so that you have the checksum already built in there, and there's a virus protection scanning that goes on before that is committed to any kind of storage. And then you can set certain access restrictions depending on what your applications are for that. And then the metadata starts to become more extensive, where you're putting in admin logs. What's happened to this data? Where did it come from? When was it last transformed? Et cetera, et cetera. And then you can start to build on your inventory format. So just out of the box, those are easy things to do in cloud. Now, it's possible to get all the way through all of the levels. If you look at levels 3 and 4, where that really becomes important, and this is more where the studios are operating, is this idea of DR in this case is disaster recovery. For those of you not familiar with it, you need that copy that you can get to in case all other copies fail. So level 3 just requires you have at least one copy that is your disaster recovery copy. Level 4 requires that all of those copies, and that typically has to do with where they're located, geographically separate, not in the same earthquake zone, or as they say in Washington, D.C., not within the blast zone, which is kind of scary. Which is why, if any of you have ever been to the Library of Congress archive, it's placed just outside the blast radius of Washington, D.C. So, fun factoid, scary factoid. Again, the more metadata we preserve and keep with these things, the better. Now, in terms of metadata, I just wanted to make the point, and I've heard this from Andrew on a few occasions. I'm hoping that we get to the point where what an archive consists of is the source media and the metadata that made the thing. And then from the metadata, we can recreate anything that came from the source. We're a little ways off from that, but it's entirely possible. If you refer to the Movie Labs paper, they're getting a lot of press today. You will find that there's a lot of this same kind of conversation in there, but ultimately it should be about that, and we can get back to a simpler time where we don't have to save all the versions and worry about which version, because the versioning happens in metadata, which is a much easier thing to store. Just quickly, I just wanted to point out, if you want to get to the levels 3 and 4, though, it's come up a number of times today, this idea of egress, and those, again, are conversations we're having internally. But there will be egress charges if you're retrieving files in their entirety and running new checksums on them, and then, in this case, you don't put them back because all you're doing is copying it, but it's considered an early retrieval if, for example, like if you use our cold line storage, the cadence for minimal retrieval fees is a year, that you don't touch the data more than once a year. So if your process is set up such that you're checking the fixity of your files once a year, then you're going to incur the minimal costs of trying to read those files. But the nice thing about the metadata embedded into the checksum embedded into the file itself is that the egress charges don't apply to just reading that bit of data. It applies to moving the actual data to read it, if that makes sense. Okay, and these are just currently where we're at with that. Now, it's less than a penny per gigabyte per year, but that adds up pretty fast when you have petabytes of material, and in some cases, exabytes of material we're running into. So I just wanted to kind of throw that up there, that if you were trying to get to that level 4, where you really want to read that entire file back, generate a brand new checksum for it, just to make sure it's okay, then you're going to introduce some costs into the equation. So with that, probably have time for a question or two, but I can hear Tommy's grumbling for lunch. So any questions?